So we're going to take a quick look at the double and half angle identity formulas and how to apply them to a given situation. So if we're given that the sine of theta is 8 over 17 and the cosine theta is less than 0, meaning it's negative, they want you to find sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. So what I'm basically doing is I'm doubling the angles, but it is not an equal statement to say, well, then I would double 8 over 17 to find sine of 2 theta. And this is because the angle is going to behave differently and not have a straight ratio. So the first thing we have to realize is that the formula for sine of 2 theta on the formula sheet that you have requires the use of cosine. So I'm going to look at my Pythagorean theorem, sine squared plus cosine squared equals 1, and I'm going to solve it for cosine squared. This will allow me to plug in and get my cosine theta because I can square root it. So in this sense, I'm not necessarily plugging directly into the identity for sine of 2 theta, but I am taking it and finding cosine theta, taking the square root so that I know cosine theta. You could also sketch the triangle with the hypotenuse of 17 and a y value of 8 and use the Pythagorean theorem to find 15. That's acceptable as well. The only quadrant that fits this criteria would be where sine is positive and cosine is negative is going to be encountered a little bit later. But for now, we have that cosine theta is less than 0, so that's where the negative is coming from there. Now I'm going to apply the double angle formula of 2 times sine theta cosine theta. I'm going to replace sine and cosine with their values to get negative 240 over 161. So there are a lot of times when you're plugging directly into these double angles that you're going to have to find information before you can even begin to plug into the identity. So the formula for cosine 2 theta is 1 minus 2 sine squared theta. I don't need to find any other information, but I'm going to replace the sine with 8 over 17 to be able to get my cosine of 2 theta as 161 over 289. Now I know that tangent 2 theta is sine 2 theta divided by cosine 2 theta. So I'm going to take the two values that I found and divide them to get negative 240 over 161. Alternately, you can also find tangent theta by doing the double angle identity. You would want to use the method on the previous slide if you've already found sine of 2 theta and cosine 2 theta. That's how you know when to do that. If you haven't done that, you could take this and actually divide them to find tangent, and then you could use the formula tangent of 2 theta is 2 times the tangent over 1 minus tangent squared. So you would want to use this method when you haven't found sine of 2 theta and cosine of 2 theta. Next, let's look at finding the values of the 6 trigonometric functions if I know that cosine 2 theta is negative 12 over 13. So I'm going to go ahead and utilize that cosine 2 theta identity so that I can figure out what is sine theta. So I'm going to replace that and solve, and I'm going to get sine squared theta is 25 over 26. I'm going to need to square root it, but I know that it's in quadrant 3 from the directions because it's between 180 and 270. So that tells me that sine is going to be negative. So once I square root it, I rationalize it, and I know that sine value is going to be negative. Then I can take it a little bit further to find cosine because I have multiple options here. So I'm going to use this identity. I'm going to replace the cosine value, the cosine 2 theta value, and I'm going to solve for cosine. I know it's in quadrant 3, so my cosine is negative, and I'm going to rationalize the denominator. Then to find tangent, because I found sine and cosine previously, I can simply divide those two to get a trig ratio. To find cotangent, I would do cosine divided by sine, since I already know those, and I would get 1/5. Likewise, I already know that secant is 1 over cosine, or the reciprocal of cosine, which gives me negative 26, square root of 26. Cosecant is the reciprocal of sine, So I'm going to invert sign, then rationalize the denominator to get negative 26 over 5 with 26 under the square root. Here are some additional examples of how I can utilize these functions. 2 cosine squared of 5x minus 1. If I want to simplify that, I can take that cosine of 2 times 5x, which would be 10x, because that is the equivalent of the cosine double angle identity. Remember, the cosine double angle identity is 2 cosine squared theta minus 1. So I'm taking that theta value of 5x and I'm multiplying it by 2. Then I should recognize this formula is very, very close to the double angle identity for sine. So I'm going to multiply it by 1/2 times 2, because 1/2 times 2 is really just 1. Then I can realize that, oh, this is going to be the angle identity for sine double angle, but I'm going to have to put a 1/2 in front of it to account for that missing 2. So I would get 1/2 sine of 330. If I want to write the cosine of 3x in terms of cosine x, I can make that the cosine of 2x plus x, and I can blend together my double angle and my sum identities to be able to get to the answer. So I'm going to use the fact that cosine of a plus b is going to be equivalent to this. Then I'm going to take this cosine of 2x and the sine of 2x, and I'm going to use those identities. Now that I do that, I will distribute the cosine through and distribute the sine through here. Then I'm going to make sure that I remember that cosine squared plus sine squared is 1, or that 1 minus cosine squared is sine squared of x. At which point, I'm going to distribute that cosine x through, and I'm going to arrive at this identity, but I can still factor out a cosine. So it might be general to say this would be 4 times cosine x, open parentheses, cosine squared x minus 3. And that is the multiple angle identity for the double angles. So now let's take a look at applying a few different types of word problems. Write 6 sine 40 sine 15 as a sum or difference of two functions. I know that I can make this cosine of 40 minus 15 minus cosine of 40 plus 15 to be able to get 3 cosine of 25 minus 3 cosine of 55. So I'm using those sum or difference identities to be able to form them. I can also write these as a product of functions, because I know that if I have cosine of 3 theta plus 7 theta over 2, that's going to be 10 theta over 2, or 5. And then I'm going to have 3 minus 7, which is going to be a negative value, over 2, which is going to be negative 4. Then I'm going to be able to apply my trig identities to simplify this down to 2 cosine 5 theta cosine 2 theta, because 7 plus 3 is 10, divided by 2 is 5. 3 minus 7 would be negative 4, divided by 2 is a negative 2. Now, how are the half angle identities and how do they play into this? When we're dealing with a half angle identity, more than often than not, there's a decimal that's going to be involved. So things like 22.5, that's coming from half of 45 degrees. So I'm going to use my half angle identity formula from my formula sheet, which is the square root of 1 minus cosine theta over 2. Then I'm going to use the trig chart value that I know cosine of 45 is, and I'm going to manipulate it algebraically until I can solve. Now, the half angle identities are often going to have a radical inside of a radical. That is okay. I know you don't see it happen much outside of this, but it's absolutely okay. Now, if I want to look at the exact value of tangent of 75, I could think about tangent of 75 is half of 150. So then I could plug into my tangent formula, and I can use reference angles to find what the values are. The reference angle for sine of 150 is 30, and same for cosine, but I have to remember that cosine of 150 is negative because it's in quadrant 2. Then I'm going to algebraically simplify this to get 2 plus the square root of 3. Lots of algebra happening there, guys. I can follow much the same pattern and find the cosine of the 6 trig functions if I just know one. So I'm going to use the angle associated with this as in quadrant 2 based on the information that I've been given. I'm going to know that sine is positive there, but cosine and tangent are negative. So I'm going to use the half angle identity, since I know cosine s, to find my sine of s over 2 is the square root of 10 over 14, which I rationalized to get the square root of 35 over 7. Then I'm going to use my cosine half angle identity, which again just uses cosine of s. I'm going to replace and algebraically simplify. Because I know the sine of the half angle and the cosine of the half angle, I'm going to divide those two to get my answer. And then I'm going to do some algebra to rationalize my denominator. Now I can work this in reverse. If I want to simplify each expression, I just need to identify what half angle identity is in play here. This formula matches the formula for sine of a over 2. So I'm going to substitute 8 over x for a, and I'm going to get that this is sine 4x. In the second one, this is going to be the identity for tangent of a over 2. I'm going to replace a with that 9 beta, and I'm going to get tangent of 9 beta over 2. Now, I wouldn't do 4.5 beta here because we like to have things in fractions as much as possible. Now, if I want to verify that something is an identity, I'm going to start with the right-hand side of the equation and try and turn it into what's on the left. Now, the first thing that I like to do is to always rewrite things in terms of sine and cosine, which I did. Then, I'm going to work towards getting them combined into one fraction. Once I'm here, then I can start looking at, well, what can I do to this to try and get to something I can simplify? I'm going to factor, and I'm going to factor the numerator and the denominator, which would be 1 minus cosine x over 1 plus cosine x, because I can factor and then cancel things out. Which then, and this is where it gets interesting, becomes I can square root both sides, and I'm going to get tangent squared of x over 2. So my identity is verified.